Hello all, I'm Moin and I'll be presenting Waffle, a workload aware and query sensitive framework for disk-based spatial indexing. Waffle is a disk-based spatial index that combines concepts of the space and data partitioning frameworks and constitutes a complete indexing solution. It includes a novel bulk loading method that guarantees optimal disk space utilization on static data and algorithms for dynamic updates that guarantee zero overlapping of nodes. It also includes a maintenance mechanism that adjusts the trade-off between query and update performance based on the workload and query distribution. We start with bulk loading. Waffle uses a two-step bottom-up bulk loading procedure. The first step creates all the data nodes at the bottom level by recursively splitting the space, such that all data nodes are fully packed. The second step recycles the splits from the first step to create the rest of the levels. The procedure takes two parameters, data node capacity and directory fanout. Data node capacity is the maximum number of data points per data node, and directory fanout is the maximum number of child pointers per directory node. To demonstrate the bulk loading procedure, we use the following example, where in the beginning there is a single data node and not one containing 23 data points, and the data node capacity and directory fanout is set at 3 and 2 respectively. Since node 1 exceeds the data node capacity, we partition it into two new nodes. A data node split is defined by two characteristics. First, it is perpendicular to the node's longest axis. Why? Because it helps us avoid long and narrow elongated nodes, also known as spaghetti nodes, and it gives us more square-like nodes. Second, it is at the point whose rank on the longest axis is a multiple of the of the data node's capacity, and minimizes the cardinality gap between the nodes. In this case, that is a node at rank 12. Also, note two things here. The newly created nodes are shrink to maximize the dead space, and the split sort of creates virtual containers for the nodes to expand into without overlapping each other. Next, we continue partitioning the nodes as their cardinality exceeds the node capacity. Now note that the first split in a subspace always cuts it end to end, which means all following splits and nodes are on the either side of the first split. That is, they never overlap with the first split. And to utilize this property, we maintain an ordered list of splits. Because we always partition the data node at a multiple of the data node capacity, finally we are left with all nodes except possibly the last one as fully packed. This concludes the first step of Waffle's bulk loading procedure. In the second step, we focus on creating the rest of the levels. At the end of the first step, we are left with 8 data nodes which exceeds the directory fanout of 2. So we are required to partition N11. Partitioning a directory is as simple as popping its first split and dividing the contents on its either side to the two new directories. So here the new N11 gets N01, N05, N03, N06, and the splits S04, S02, and S05. And the rest of the child nodes and splits goes to N12. And the previous node's first split becomes the new root N21's first split. Now since N11 and N12 contains 4 child nodes each, we further partition them in the next slide on the first split respectively. After further partitioning each directory at height 1 holds 2 data nodes, which is the fanout in this example. So that concludes the second level of the tree, and as a reminder, the splits used for partitioning are moved to the parent nodes list of splits. Here we should also note that because we recycle the splits that were made originally to create square-like data nodes, they implicitly help create square-like directories as well. Moving on, N21 now exceeds its directory fanout, so we partition it in the next slide on its first split S11. And with that, we have two new nodes N21 and N22 that shares the contents of the old N21. The first split S11 used to partition the old N21 is now added to the split list of the new root N31. And this concludes our bulk loading procedure. Notice that we do not perform sorting or any similarly complex operation after the first step involving the data nodes. We simply iterate over the nodes and splits and separate them using the old nodes first split. Next, we move on to dynamic updates. The procedures used in dynamic update are similar to the bulk loading procedures. The data nodes are partitioned on the longest dimension to get square-like nodes, and the directories are partitioned on the first split. This guarantees that the split does not intersect with any other node. Dynamic updates in Waffle also guarantee zero overlapping of nodes. First, we see how Waffle selects data nodes when inserting points. As discussed before, the splits create virtual containers for each node to expand into. So when inserting a new point, we select the node whose virtual container covers the point, possibly expanding the node within the constraints of the container. And this allows us to guarantee zero node overlaps. Next, we discuss how we handle node overflows. To demonstrate the same, we use the example where the directory fanout is limited to 4. Say data node n node 2 has overflowed and we are required to partition it. So to partition the data node, we first sort its contents on the longest dimension and create a split on the median. After partitioning, N11 has 5 data nodes which exceeds the directory fanout 4. So now to partition the directory N11, we simply choose its first split because by design it cuts the subspace end to end and without intersecting any other node and having all other child nodes and splits on its either side. So we can very conveniently separate the contents. And thus the new N11 gets N01 and N03 along with the split S02, while that new node N12 gets N02, N05, N04 and the splits S04 and S03. And split S01 used for the partitioning of the old node N11 now becomes the first split S11 of N21. And this concludes how we handle overflows. After splits or deletions, nodes may have relatively few children, leading to a large number of half-full nodes. Now, half-full nodes are good for insertions as they don't quickly overflow, but on the other hand, they are bad for querying because it leads to higher number of node accesses. R star trees always reinsert a subset of data points to improve the index structure and enhance the efficiency of future queries before partitioning an overflow node. And on the other hand, KDB trees do not include any such maintenance procedures, which allows quick updates but at the expense of query performance. Waffle takes a more flexible approach where it monitors the query workload subjected to individual queries and regulates the read-write trade-off accordingly. Waffle uses two metrics to evaluate the need for maintenance. First is FAT, which measures the deterioration of directory N based on the number of data node it contains compared to the optimal number. Second is tolerance, which is simply the ratio of number of write to read operations encountered by the directory. Note that Waffle only monitors these values for directories at height 1 because it gives very fine-grained control over the data. The key idea here is that whenever FAT exceeds tolerance for a directory, Waffle reloads that directory, that is, it performs a local bulk loading procedure only on that directory to reset its FAT to 0. In more detail, this is the maintenance cycle for a directory. Let's say we begin at a read favorable state where FAT is equals to 0. This is the same state Waffle starts when fully bulk loaded. In this state, read operations are most effective. And even if there are write operations, as long as they don't result in node splits, Waffle remains in this state. With more frequent write operations, which leads to node splits, the FAT may become higher, and in which case we go to a write favorable state. Waffle stays in this write favorable state as long as FAT remains below the tolerance limit. With more read operations, it is possible that tolerance may come down and FAT may become higher than it. In which case, Waffle locally bulk loads that individual directory specifically so that it can restore its FAT to 0 and again come to a read favorable state. Next, we move on to experimental evaluation. Note that we cover many experiments in the paper, but in the slides we only focus on a select few. We use two datasets, OSM, the OpenStreetMaps dataset. However, in this case, it only focuses on the United States. It contains 70 million data points. Second, AIS, which is a dataset of ships located across the globe. It contains 100 million data points. We have three competitors, RBoost, which is the label for Boost's bulk loading algorithm, which is a combination of STR and TGS. Second, KDB-tree, and third, Quadtree. To give a preview of the quality of partitions, these are snapshots of data node extents of various bulk loading procedures when employed on a sample of 10 million data points from AIS. As you can see that a good index should give a good visualization of different trajectories taken by ships across the globe. We can clearly see some of those trajectories in Waffle due to its more square-like shapes. However, RBoost, which uses STR, that uses tiling approaches, you can see that it produces many spaghetti-like nodes, which are not good for range queries. We also have a small table where we measure three different metrics: number of data nodes, average number of points per data node, and average data node parameter. In each of these three cases, Waffle produces the most desirable values. First, we look at the size chart. Note here that Waffle also includes splits apart from the data nodes and other nodes, and which is why it weighs more than RBoost despite having similar number of nodes. Whereas in KNN queries, Waffle is outright best because of better partitions, and for range query performance, the difference is very little across indexes because it's mostly a feature of the number of data nodes. Next, we move on to experimental evaluation for dynamic updates. Again, we use the OpenStreetMaps dataset. We used RStar trees by Boost, labeled as RBoost as one competitor and KDB-tree is the other competitor. The experimental procedure is divided into two steps. The first step stabilizes the indexes based on the experiment profile. Since KDB-trees and R-trees cannot adjust to workload or distribution, we simply insert 10 million data points as part of their preparation. On the other hand, for Waffle, we insert 10 million data points and execute queries according to the experiment profile. In the second step, 1 million further insertions and the corresponding number of queries are performed for all indexes as per the profile. Index performance is only evaluated in the second step. The profile for these experiments is spatial distortion, which means the order of insertions and queries is random, and 90% of the queries are concentrated in three regions, and the remaining 10% in the rest of the dataset. The three regions are centered around Los Angeles, Chicago, and New York City. We also have three different kinds of workloads: write heavy, which means 10 insertions for every query; equal heavy, where we have equal number of insertions and queries; read heavy, where we have 10 queries for every insertion. First, we see the plots on the left, which measure only the query cost of the indexes. First, we have the so we see that Waffle has better query performance than other indexes for both KNN and range, and that's mainly because of better node shapes and individual focus on directories that are subjected to more read-heavy workloads. And on the right, we measure the total cost, which includes query cost, insertion cost, and any maintenance cost. For RBoost, the maintenance means reinsertions, and that reinsertion cost is already a part of the insertion cost. For Waffle, the maintenance cost means the local bulk loading cost, which is labeled as reload cost. First, we'll look at the KNN queries on the top right. The KNN queries don't require many data nodes, many data node accesses, which is why insertions become more significant in overall cost. And because RBoost necessarily performs reinsertions, even when it's not beneficial, it suffers the most of all indexes in write and equal heavy workloads. On the other hand, KDB trees, which ignore maintenance altogether, perform the worst for read heavy workloads. And Waffle, on the other hand, only performs maintenance depending on when and where it is required, and therefore comes out as best for all workloads. The picture is pretty much the same for range queries, with the main difference that the significance of insertion costs has dropped due to range queries requiring a lot more data node accesses. To conclude, Waffle is a disk-based framework that aims to optimize performance for all spatial indexing purposes. For static data, Waffle achieves the minimum number of data nodes through a fast bulk loading algorithm that avoids cascading splits. The output node extents have a desirable shape that minimizes their average parameter. For dynamic data, Waffle automatically adjusts the balance between node packing, and update speed. Depending on the setup, local bulk loading reorganizes subtrees on the index that iterate after updates. That's it for this presentation. Thank you.